Hello everyone, I'm Yayun. I obtained my PhD in robotics and control from UCLA. Currently, I'm a postdoc at Northwestern University. Today, I'm going to present modeling the locomotion of articulated soft robots in granular media. Locomotion in granular media, such as sandfish lizards, who use large amplitude traveling wave oscillation of their body for propulsion in sand, inspire scientists and engineers to develop articulated robots in granules to understand the underlying physics. An interesting discovery is that resistive force theory, also known as RFT, can be applied in granular media, which is surprising because RFT was originally defined in viscous fluids. Dr. Taxia explored rigid, articulated locomotion in granular media and used RFT to model the hydrodynamic force from the granules onto the tail of the robot. In contrast, we aim for a simple test bed to explore articulated soft robots in granular media. Inside our robot head, there is a motor, a battery, and a microcontroller. Soft elastic rods are attached to a 3D printed plate, which is actuated by the motor shaft sticking out of the head. To fabricate the elastic rods, we mixed the two polymers and injected the mixture into PVC tubes, wait for about 20 minutes for it to cure, and then demolded. The robot is placed in a tube full of transparent water beads, making it easy to see the movement of the robot. Then, we started to explore the modeling of locomotion of articulated soft robots in granular media. The modeling is challenging as it couples mechanics of articulated elastic rod structures and the model of external loading from granular media. Our modeling simulation is based on discrete differential geometry, or DDG. As the name of DDG indicates, the robot structure is discretized into a series of rods by geometry, consisting of nodes and edges. Thus, the elastic energy of the robot is a linear sum of bending, twisting, and stretching energies of each node. The degree of freedom of an n-node system includes the XYZ position of each node and bending angles of n-1 edges. According to Newton's second law, for each degree of freedom J, the elastic force, which is the negative gradient of elastic energies plus external forces, is equal to ma. Therefore, there are 4n-1 equations of motion for 4n-1 degree of freedoms. Note that this external forces is the hydrodynamic forces we are going to model next. Stokes' law tells us the hydrodynamic force and a moment on a spherical robot head, as shown in the rectangles. But our robot head is not exactly spherical, so we use CT and CR as fitting parameters, where T stands for translational, R stands for rotational. According to RFT, the hydrodynamic force on flagella is equal to the minus drag coefficient along the tangential direction of the velocity at each node, multiplied by the corresponding velocity minus the drag coefficient along the perpendicular direction of the velocity, multiplied by the corresponding velocity. Here are some experimental results. As you can see from the experiment video, when the robot moves to the right at a constant velocity v, the robot head and the tails are rotating in the opposite directions at a constant rotational speed omega h and omega t respectively. We denote the sum of them as omega capital T. Then, there are two control parameters in the system, total rotational speed omega capital T and number of tails n. Next, we are going to explore the relationship between the robot performance versus omega capital T and n. From experiments, we found that omega t has to reach a threshold before the robot can start to move. Then we plot the experiment data of the robot position versus time. Then we linear fit the experimental data, and then the slope here denotes the robot moving speed. When the n increases from 2 to 4, we found actually that sometimes the robot gets stuck in the same position for some time, and then this is called jamming or stick slip. As previously mentioned, we use RFT to model the hydrodynamic force onto robot tails. We use the fitting parameters CT, CR, and mu, where mu stands for the drag coefficients of granular media onto the robot tails to fit experimental data and simulation results for two-tailed robot about normalized speed of the robot v bar versus normalized total rotational speed omega t bar and normalized rotational speed of the robot head omega h bar versus omega t bar. And then the same set of fitting parameters is used to predict the performance of a three-tailed robot. The simulation results match quantitatively well with experimental data. One interesting finding is that at the same omega t bar, the two-tailed robot actually moves faster than the three-tailed robot. So as number of tails increases, robot speed decreases. Then our simulator is used to predict the efficiency of actuation versus omega capital T. As you can see, the efficiency of a robot with n is equal to 2 is non-monotonic and it reaches the maximum when omega t is about 150 rpm. At this rotational speed, the robot moves the furthest per unit torque from the motor. Moreover, there is an intersection between the efficiency of a two-tailed robot and a three-tailed robot. These observations underline the high nonlinearity of the system and highlights the need of our numerical simulator that can be used as a design tool for this class of robots. If you still recall, experiments show that two-tailed robots swim faster than three-tailed one. But why? It's sort of counterintuitive, as the more tails, the more propulsion. We carefully checked the videos and found that it's probably because of the fast rotation of the robot head. Hence, in our simulator, we increase the drag on the robot head to slow down its rotation and predict that there should be cases where two-tailed robots run slower than three-tailed robots. Again, showing our simulator can be used as a design tool. Actually, later by the experiments, we show that the cases do exist. Alright, it's time to summarize my talk today. We talked about our contributions to modeling the locomotion of articulated soft robots in three aspects. First, we showed a unified simulation framework incorporating differential geometry and external forces. Since geometry and forces are mainly evolved, the same framework can actually be applied to the moments in fluids as well. Second, we displayed a simple untethered robotic testbed in granular media. Third, we showed that RFT can be applied to the moment in granular media, but also has its own limitation. For example, it cannot model the jamming. Finally, we want to thank our funding agencies, NSF and UCLA Startup Funding. I'm so sorry that I cannot attend the conference in person, so if you have any questions, please feel free to email me, or you can find the link to my LinkedIn on my personal website, yayun.com. Thank you.